start, the sooner we can get done, and then just relax, right? All right. So you guys should have at least looked at 8.1 on your own. I'm going to just kind of go through briefly and do a little bit of like overview and a little bit of notation stuff from that section just to make sure we're all kind of at the same point. But it'll be pretty quick, and then we'll just kind of get going into 8.2. Sound good? All right. So in 8.1, we looked at like 3 representations of a vector. So you had like magnitude and direction. You had head and tail, like as points. And then you had component form. And then we would have talked about kind of how to move back and forth between these 3 forms. So for your head and tail, you would be, gotta do that. You'd be given like a coordinate pair where like you have a coordinate for the head and a coordinate for the tail. To go to component form then, the x is going to equal the head minus tail and for each component. So here our vector v would have been represented by 2 ordered pairs. One indicating the head of the vector, that's the part with the arrow, and the other part indicating the tail, that's the straight end of the arrow, right? Here, for magnitude and direction, usually we represent the magnitude of the vector by putting the vertical bars around the name of the vector. So there is no absolute value for vectors, just to be clear. The absolute value of a vector is nonsense. When we put the vertical bars around a vector, we're talking about magnitude. In the notes, rather than using that vector hat like I'll do when I'm writing, typically we use boldface to indicate something as a vector as opposed to a variable or whatever. So keep that in mind when you're reading the notes or whatever. Obviously, I can't write boldface on a sheet of paper, so the notation I use, I put that little vector hat on top of it. And then our direction, I'm just going to use like an angle variable like theta. So to go to component form then, x is going to be magnitude times cosine of theta, I guess, provided theta is a standard form angle. And y is going to be, bless you, the magnitude times sine theta, again, assuming that theta is a standard form angle. When I say standard form angle, you guys know what I mean? That it's measured from the positive x-axis rotating counterclockwise. as opposed to like a bearing or something, right? Okay. So typically, oh, and then we should talk about how to go back from component form to magnitude and direction. Well, fortunately, that's easy. So the direction we can find by doing the tan inverse of y over x. I put a double asterisk there because you might have to add or subtract 180 degrees depending on the quadrant that the xy is located in. Maybe I should say 180 or even 360 degrees, I guess, depending on the quadrant. Just like we did in first semester, right? When you found the inverse, depending on the quadrant that we were located in, when you did the inverse on your calculator, you might have had to add or subtract, 180 or 360 degrees to get the correct angle measure. And then, yeah. So that's about it. Typically, we don't go straight from head and tail notation to magnitude and direction. There's really no reason we'd ever want to go backwards from component form or magnitude and direction to head tail. And really, the gold standard in terms of doing any algebraic work with vectors is we want component form. It's the easiest one to manipulate algebraically. And typically when we spit out answers, we like to give our answers as a magnitude and direction because often those have meaning in the physical world in a way that like a component form notation doesn't. So more often than not, the first step in any vector problem is going to get everything into component form. Then we can manipulate things in component form. And then we can change it back into a magnitude and direction at the end to represent our answer. And that was the big takeaway from section 8.1, was just moving back and forth between these three different forms. Does that feel okay? That sounds like what you read, I hope. Again, just wanted to kind of reorganize and like summarize it in one big fell swoop. Some of you may have gotten further than others in terms of reading and going through that. So I just wanted to make sure that we were kind of all on the same page before we started the next stuff. So next we'll talk about vector operations, and the big thing to keep in mind when we're talking about vector operations is we're really just going to be using component form to do all of our vector operations. So that's something important to kind of keep in mind. And you'll see why when we start defining how to do addition, subtraction, some of these multiplicative-ish operations, why component form is so nice, because really everything is very simple to do in component form. But we're just going to kind of bulldoze through here and do a bunch of definitions. So the first thing we'll define is the 0 vector. We denote the 0 vector with the number 0 with the vector hat on top of it. Important that you have the vector hat on top of it, because you can't add a vector and a real number. You have to have, if you're going to add a 0, you have to be the 0 vector. You know what I mean? And the 0 vector is obviously the component form vector 0, 0. So that vector has a magnitude of 0, and it's the only vector that has no direction, which is fine. When we talk about real numbers, there is one real number, for example, that has no multiplicative inverse. That number is 0, right? Because the reciprocal of 0 is undefined. So similar kind of thing here. Even though we say that all numbers have a multiplicative inverse, that's not really true. All vectors have a magnitude and direction. Well, that's not really true. This is the one vector that we're allowing to have no direction. So next definition, we're going to let U be the vector U1, U2, and V be the vector V1, V2. I apologize that my U's and V's look similar. My U's definitely have a tail, my V's do not. So we say the sum, or some places use the term resultant. So to add two vectors in component form, super simple. You just add the x components together and you add the y components together, which is super lovely, right? Geometrically, what is that really saying? So if we have one vector, let's call that v, and another vector, let's call that one u. If we did v plus u, we have our vector v, and then we have like an imaginary xy axis, and then we just draw like our vector u, starting at the head of vector v, and then this would be like our vector u plus v. To just give you a little bit of additional like geometric interpretation of what it is that we're doing here. That's called the head to, or the tail to head representation or whatever. So again, that's just geometrically what addition is saying. Okay with that? And as we're doing this, I'm going to continue to try to give some geometric representations. I think that's helpful to just kind of build some intuition about what it is that we're actually doing and what this means, right? Pictures usually say a lot. Oftentimes it's helpful to visualize something that's going on. So next up. Okay, the scalar product of a scalar, in this case k, when we talk about a scalar, we're just talking about a real number. So I have k as a member of the real numbers there. And the vector u, we write as just k times u. And basically all we do is we multiply that scalar to each component. So geometrically, if this is U, then like that's 2U. It's basically just U stacked on top of itself. Everybody's okay with that idea? How's that? It's good. Okay. So scalar sounds like the word scale, right? If you draw like a scale drawing, you're basically taking the same image and shrinking everything down or expanding everything out by some factor. That's exactly what scalar multiplication is doing here. It's basically just taking the vector and shrinking it or stretching it by some factor, right? That's the easy way to kind of remember that. Okay, so just some quick numeric examples here to buzz through. So let's say we wanted to do U plus 2V. Well, I'll just draw or write in the values there. I'll do my scalar multiplication. And just like you'd suspect, the order of operations for vectors is the same as the order of operations for the real number, so you have to do the scalar multiplication before you can do the addition. No shock there. What do you guys think? Pretty straightforward? No surprise there? Okay. Let's just move on. We don't need to do a bunch of those. Oops. So the vector additive inverse of, say, some vector u, we write as negative u. And as you might suspect, it's just the opposite components of the original vector u. So geometrically, if this is u, that's negative u. The vector's the same length, it's just going kind of the opposite direction, right? Everybody feel okay on that idea? Fairly straightforward, right? Hopefully that's not much of a surprise. We say a unit vector is a vector is a unit vector, if and only if its magnitude is 1. Again, remember the vertical bars here mean magnitude, not the absolute value. And unit vectors will become particularly useful to us because they can really serve as a proxy for direction. Remember that the way we calculate the magnitude of a vector in component form is just by taking the x component, squaring it, plus the y component, squaring it, and then square rooting it. And we know for a fact that cosine squared theta plus sine squared theta is equal to 1. So this just basically allows me to capture the direction of a vector without concern of its magnitude, because in this case the magnitude would just be 1. So that'll come in handy later, but I just wanted to point out to you now. Okay. So given the unit vector v, given the vector v, we can find a unit vector in the same direction of v by taking the reciprocal of the magnitude of v and scalar multiplying that to v. So here's our v. There's our u, where u has magnitude 1. It basically is just shrinking it down. The orientation, the direction of that vector stays the same. We've just shrunk it down to to have length 1. Let's look at a numeric example of doing that. Just to practice. So let's say we're asked to find a unit vector in the same direction as this vector v, which has component form 5, -6. I'm going to need the magnitude of v I want to point out here for just a second that remember the square root of 25 plus 31 is not the same as the square root of 25 plus the square root of 31. That square roots don't distribute across addition symbols, so you can't just turn that into 11. Okay? I say that and you look at me like, no doy, but people do that every once in a while. They get stressed out or confused or turned around, and it's an easy mistake to make. So I'm just pointing it out and reminding you now, so that when you're tempted to do it later, maybe you think back to this moment and go, oh yeah, Mr. Kulik told me never to do that. So u is square root of 6 times the vector 5, -6, which just becomes 5 over the comma -6 over the square root of 61. And typically we don't like to leave those square roots in the denominator, so we'd like rationalize the denominator there. And write it that way. Do we feel okay there? Okay. Now there's two unit vectors in particular that are very special to us. They're called the standard unit vectors. Give the name, those are the standard names we give the unit vectors, where I is the vector 1, 0, and j is the vector 0, 1. So with that, we can take any vector and rewrite that in terms of unit vectors. So for example, if v is the vector cd, we can write v as the vector 0 or c0 plus the vector 0d. And then we can c0 would be the same thing as c times the vector 0, 1. I'm sorry, 1, 0. Be the same thing as z times the vector 0, 1. And 0 or 1, 0 and 0, 1 is just the vector j. So in this case, we could represent v as the vector ci plus d or plus dj. This form we give a special name to. We call that the okay. So again, this linear combination form just gives us another way to represent a vector, right? That's at this point, there's not really anything that we're going to do with that right away, so just kind of tuck that away in the back pocket. That's all it really is. It's just another way of representing a vector. We'll probably come back to that a little later on, and it'll become more useful later on, but for right now, it's just going to just be something that we have. Our last matrix operator we're going to talk about today is called the dot product. Come on. What is going on? So the dot product of u and v is just going to be u1 times v1 plus u2 times v2. Note is a scalar, so the dot product of two vectors is just a number. It's not another vector. Okay, and we'll be using dot products a lot in this chapter as we move forward. Or maybe it's in the next chapter. I don't remember for sure. I think it's this chapter though. When we talk about lines and planes and such, that'll become quite useful. So let's look at some properties of dot products. So some of these we're going to prove sizes. So the first one is that the dot product of it is commutative. The second one is that the zero vector dot product with anything is just the number 0. And then there's the distributive property that works just like we'd expect it to. And then we have the scalar associative property. So for scalar C, it doesn't matter when you kind of apply that scalar. So you could apply the scalar to the vector u and then do the dot product. You could apply the scalar to the vector c and then do the dot product. Or you could do the dot product and then apply the scalar c. One is the magnitude property that says if you take the dot product of a vector with itself, you get the magnitude squared for that vector. So let's do a couple of examples here. So let's say u is the vector 3, v is the vector -1, 5, and w is the vector 8i plus 4j. So if I wanted to do u dot v, I'm going to do the product of the x components plus the product of the y components to get -17. Okay with that? What if I tried to do w dot v? Notice that those are not in the same form, right? One is in that linear combination form and the other is in component form. I would just start by writing the linear combination form into component form. So basically the coefficient on the I tells you the x coordinate and the coefficient on the j gives you the y component, right? No big deal there. So once we've done that, then 8 times -1 plus 4 times 5 is -8 plus 20, or 12. What do you guys think? No big deal? Just a different operation. You just have to remember the formulas. So one use that we have for the dot product is it allows us to calculate the angle between two vectors. So the angle between those two vectors is going to be the cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. So just worth pointing out, here in the numerator, that one is a dot product. Down here, this is just multiplication, because the magnitude is just a number, right? Is everybody okay with that idea? We're going to prove this formula here. Now again, with a proof, would I expect you to be able to repeat this? No way, Jose. But I think it's useful in terms of this being an honors course and you guys developing some kind of intuition about like how these things are done. So let's say we have two vectors here, u and v. And we're looking for this angle theta here. Okay? What I'm going to do is I'm going to make a triangle by adding some vector to u. What vector would I have to add to u in order to get vector v? It seems like a weird question. You're like, how the heck would I know that? When I write the answer here, you're going to go, oh, der. Well, the vector would be u minus v, right? U plus u minus v, or v minus u, has to give me v, right? Did I say it wrong the first time?
You said u minus v.
Yeah.
You wrote down v minus u, and I was like, wait.
I wrote the right thing. So that's what I'm going to do. Everybody's okay with this picture where the v minus u comes from? And now what I'm going to do is I'm just going to use the law of cosines. So the hypotenuse squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. Everybody's okay here? What I'm going to do next is I'm going to use this magnitude of two vector or magnitude property. So I have this on the left-hand side of my equation where I have the magnitude of v minus u squared, right? I'm going to use that to write that as the dot product of v minus u with v minus u. So then I'm going to use the distributive property for dot products to basically FOIL out the left-hand side. Gives me v dot v minus 2 v dot or u dot v's plus u dot u, and then equals that all that other junk over there. So far, so good. V dot V is the magnitude property again. And U dot U is also the magnitude property again. So if I subtract, oops, I got the squared on that. Those from both sides, all that stuff just drops out of there for me, which is rad. And then if I divide both sides by 2 times the magnitude of U, the magnitude of V, I get that. And then if we take the cosine and inverse of both sides, we're done. Feel okay with that? Let's do a numeric example to just kind of drive this idea home. So we can write down our formula straight away. Everybody's okay with that? All right, just recopy the formula. And now I'm just going to do off to the side each of the 3 parts in my formula. So there's 3 calculations I need to do, right? U dot V, the magnitude of U and the magnitude of V. So U dot V, 7 plus negative 6 times 2, which is 14 plus negative 12, which is 2. The magnitude of U is the square root of 7 squared plus negative 6 squared, which is square root 85. And V is square root 2 squared plus 2 squared, or the square root of 8. When I type all that into my calculator, I get about 85.60 degrees. Might be geometrically worth just kind of sketching a picture to make sure that 85.6 makes sense, right? If we're talking about the angle between 2 vectors, we should be able to graph those 2 vectors. So U is 7 over and 6 down. So whatever, like there. And U is 2 over and 2, or V is 2 over and 2 up. So there. And that certainly looks like around 90 degrees, which is the result that we got. So that makes good sense to me. I feel pretty good about that answer. Do you guys agree? Again, usually it's worth just sketching a quick picture to make sure that, like, yo, I got like 115 and there's no way that should be an obtuse angle when I draw the picture. Like, that's often quite helpful. as a checker, because if you make a mistake, it'll usually be something that's like bonkers when you look at the picture. So, all right. Okay. So, what happens if theta is 90 degrees? What if we're looking for the angle between two vectors and that angle is 90 degrees? Because that's a special angle, right? Oftentimes in the real world, we're interested in when things are interacting at 90-degree angles. It's not hard to imagine why that would be useful or why that would be important. Well, remember that the cosine of theta is 0, right? So that would imply then that u dot v over the magnitude of u times the magnitude of v should also equal 0, right? And a fraction equal to 0 that becomes a new definition. So we say u and v are orthogonal, 90-degree angle, if and only if it is equal to 0. I want to make the special aside, zero product property does not hold for vectors. So just because u dot v is equal to 0 does not mean that either u is equal to 0 or v is equal to 0. So I just want to aside, or say that as an aside. That's not necessarily true. It could, I mean, certainly the one direction is true. If u is 0 or v is 0, then their dot product is 0, right? But that doesn't necessarily have to be the case. It wouldn't be hard geometrically to say this is u, clearly a non-zero vector. Here, that's at a 90-degree angle, right? So you don't necessarily have that zero product property working for dot products. I see somebody every year try to use that, and I want to make sure that I just make a special point about saying that it doesn't work. It works one direction, the trivial direction. It doesn't work the good direction that we would find useful. So let's do a quick numerical example of that. So to show these two vectors, all is show their dot product is 0. Oops, that's multiplication, is 0. Okay. Let's just stop here. Who's tired? You guys ready to be done? We've done enough.